Welcome to solverfy.
In this problem, we have three different materials with three different indices of refraction, N1, N2, and N3. We're given that the indices of refraction are N1 equals 1.55, N2 equals 1.6, and N3 equals 1.33. We're told that light with a vacuum wavelength, lambda, of 612 nanometers is going to be incident coming in from the left here. And we want to know what thickness L of the middle layer will give us maximum reflection. And more specifically, we want to know what is the third thinnest thickness, if that makes any sense, that will give us maximum reflection. So we'll get to exactly what that means in a little bit here. So in order to have maximum reflection, what's going to happen here is part of the light is going to reflect off the first surface, which is labeled here as R1, and part of it's going to reflect off the second surface, labeled as R2. So it's going to transmit through the third and then bounce off this back surface here. And these two rays are in general going to be phase shifted from one another. So in order to have maximum reflection, they have to be in phase with one another. And that means that the path length difference between these two rays has to be some multiple of the wavelength. So the path length difference here is twice this thickness L as you go once going to the right and then once back to the left. So 2L is the path length difference, and that's going to equal some multiple of the wavelength lambda. So I'm going to write that as m, and m is some integer, times lambda. Now we have to be careful. This is actually lambda in the material, so I'm going to label it lambda sub n to indicate that this is lambda in the material with index of refraction n. In our case, it's going to be n2. They want the third thickest, or the third thinnest layer. So that would be, the thinnest would be if m equals 1, then it's m equals 2 would be the next thickness that would give you maximum reflection, and then m equals 3 would be the next one. So we're going to end up setting m to 3 here. There's one more thing we have to take into consideration, which is that if you're going from from a lower index of refraction to a higher index of refraction, the reflected ray comes off phase shifted by half a wavelength. So we have to check for that. So as we go from N1 to N2, we're going from lower to higher. So that means we're now off by half a wavelength. So we're going to have to either add or subtract half a wavelength here. As we go from N2 to N3, we're going from higher to lower, so there's no phase shift on this reflection. If there was a phase shift, then we'd have twice a phase shift of half a wavelength, which is amounting to a full wavelength, which is the same as no phase shift. So we wouldn't have to consider it. But we only have one surface that's doing the phase shift here, so we've got to add, and I'm going to subtract instead of adding, lambda n over 2 here, so that now these two come off in phase. And the reason I'm subtracting instead of adding is so I can still count m starting at m equals 1 rather than m equals 0. So in total, we're going to have that 2L equals lambda n, and lambda n is just the vacuum wavelength over the index of refraction. So this is going to be lambda over n2, since that's actually the material that this is happening in, times m minus 1/2. And so now we just divide by 2 to find that L equals lambda over 2n2, and m we said was 3 because they want the third thickness. So this is 3 minus 1/2. And when we plug all these numbers in, we get that the thickness for maximum reflection is 478 nanometers.